Hello, good day. Today I would like to discuss about math, the principles of math and reasoning and abstraction in math and how to combine this with imagination. Trigger for this train of thought comes from one YouTube video by 3 Blue 1 Brown about dandelion spheres or focus spheres, which basically is a collection of 3 different proofs for those spheres. That is, how can you reason 2 properties of ellipses? First is the eccentricity, that is how squeezed the ellipse is, and the second is about the 2 points, focus points in the ellipse, that around which if you draw the ellipse, you would always have a constant sum between the distances, such that those distances are formed between the point on the ellipse drawn to both of those focus points. And the important part here is the constant, that it's always the same. Now, although I already watched the video yesterday and now I watched the ending part, the last 30-40%, I have my own take on this. So, here we go. You see, when you're using spheres, which are not there initially or originally, that is, you're using imagination, you add some extra objects, it's extra spheres, extra something that is geometrically addressable, right? And while you're doing it, and you're adding something as simple as sphere, because it can be described only by a single parameter, which is radius. You don't need any other lengths or angles, just radius, and you can say anything about the sphere. That's why it's so unique. I mean, I think that's the thing. You have pi, but pi is a constant, right? Even though you consider pi is also reasoned very in a complex manner to trigonometry, but as for now, take it as a constant, and you just need the radius to define anything about the sphere, right? Although in segments you have some heights as well in the middle, but just for the object itself, right? If you had a triangle, you need more information than that. Or if you had any other object in 3D. So sphere would be like a perfect one. But beyond this idealism for this mathematical shape, actually it's not a shape, let's say object for a moment because it's in 3D. If we take one sphere, and we call this the primary one, the initial one, the originating one, and not just see how it relates to the cone inside the, or that is cut with a plane that is going to form an ellipse, but we see that we don't have just 2 spheres, but we have a sphere and a copy of this, right? So it's not just having 2 separate objects, but you have an object which is first scaled and second translated, or vice versa. I would say first you translate it, then you scale. It's easier to understand. Otherwise it would have like inside the sphere, the initial one, you wouldn't see it. Well, it's difficult maybe to imagine, so just first copy it, right, translate it, and then scale it into a smaller one, meaning that we still use the same type of object. Now what's magical about this is that these 2 spheres have the center points which are connected by a line which also happens to be the center line of the cone. That is, there is one frame of reference, just one single axis, by which you are connecting 3 objects. The primary sphere, the secondary sphere, and the cone itself. And now what's more, why you can utilize this is that if you now draw a topology, how things are connected, like we have a sphere, let's say we have an axis that is connecting a sphere, a smaller sphere, which is a copy of this one, so there is connection here, and a cone, which is the so-called, how to say, that cone is the connector of all, but not just like throwing the links everywhere, but such that now this cone has a property called an edge, and this edge is now tangent with these two spheres at different points. That is, we are now taking this cone and we're taking this into parts. Let's say we have a bottom and we have edges, and we now said only edges are connected with the two spheres at 2 points. So we're just playing with planes, points, tangent or as tangential intersection points, and we're playing with the radiuses in the circle, and we have an axis that connects the objects themselves, the center points of those objects. Meaning that you can now connect these three objects. Just, I don't know, if you're trying to prove something about ellipses, yes, you can use the object copying and translation and rotation operations only to define the entire thing. Although I would say that this summing would be easier because that's highly linear. Let's say it's linear. That is, it just have a simple sum of two lines. It's like as simple as it can be, right? But this simplicity is optimized only for proving the ellipse. What I'm proposing here is that we have different objects and the copying property and the geometric operations with something that connects them all, and not just connects them like this, but let's say loops them in the connection, because at least one object has a property or a feature that is going to be connected with the other existing objects. That is, you're like having a feedback, which means that, oh, that's the thing with equivalence, isn't it? Because if you had topology in an abstract domain, then you can take or reason equivalences by the feedback loops. It's just how you're going to define those topologies. They are preferably as basic and definition based as possible. That is, you do not take theorems as the basis, even though that's what you would call learning, because you can abstract even more, right? But definitions themselves, like what is point, what is line, what does it mean to be tangent to something else? The radius, which is used to define a sphere. So you're already including dimensionality. Not just like a line, but a line that can move around itself in one plane and then have like kind of 3 degrees of freedom around one point, and you can draw a sphere from it, right? Or simply put, just draw a circle and then rotate the circle around itself, and boom, you have a sphere as well. But that's already a secondary operation. That would be like a theorem in that case, because you are applying what you already reasoned as the baseline for new reasoning, right? But if you took the definition itself and you based all your equivalence in respect to that, then you can come up with much greater generalization. That is, your imagination for the abstraction and for the object type shifts and copying and some interlinking between them. And voila, you can create new theories. Whoa. I mean, it's like, sounds very abstract right now. I'm not going into like actual like math here, but it can be done. It's like meta mathematics. It's just on a very low level. The basics of the basics. And yet what you're doing is just so simple. It's just moving some stuff around, and you see how those things are now connected let's say we have like different viewpoints, like in UML, I would say. UML for math, right? Or math UML. Mathematical Universal Modeling Language for creative reasoning. Or math for a generalist. Right. And even though it's so ideal, as it is usually in math, it always aims for perfection. I would even say that's now a hypothesis here. Every time Every time you have something reasoned only by definitions, and everything that is equivalent by definitions only, can only work, so to speak, or can only exist in purity, and it will always be pointing at perfection. But if you go with theorems and proofs, actually they're just different forms, they're alternative ways, kind of like linking those definitions, building another abstraction from it. But what about real life? You could say that everything in real life is pointed towards that perfection by physics or laws of physics. And it's not a necessity to actually reach it in practical world, but just to understand that that's just a set value. You will always have an error, always some misplacement, always something missing or something in excess. But that's the entire point. Because if everything was already perfect, then what would be there? There would be no motivation to carry on, right? You would only be thinking in your own capsule. But if you had this error-rich environment, then you have to, if you want to now really use energy in a flow state, then you really want to make your time well spent. That is, you want to become as lazy as if you were in pure world. Then you have to not just have a set value like this, but work towards this perfection. And the closer you get to this, the lazier you can be. Because the first principles are doing the work for you. That is, you see errors only as triggers for greater abstraction that allows you to save more time for whatever you want to do. Not just only abstracting all day long, but living life. But you can also... What was my point? Sorry, I was like... moonshot away, right? At least in my mind. Greater concepts, greater abstraction. Back to the point. Errors, right? You don't just get triggered by errors from the environment for greater abstraction to have more time, but you're also saving time from all the hassle dealing with those errors in the first place. Get it? So error as a trigger for abstraction, so that it wouldn't exist as a hassle or obstruction for train of thought in practicality. Get it? Or simply put, easily said, you see something being wrong in the world, and the more it is by first principles, the more you can approach it by definitions and purity, the more difference you can make. The more you can solve the problem by its root cause. Of course, we have like society and regulations and all this like practical life pressuring on, because some people first are not either mathematicians who are at the tip top, or who just like things to work as bad as possible so that they could benefit from these errors, as the error itself was a profitable. Anyways, goes a little bit off topic. In summary, number one, getting triggered by focus spheres and tantalum spheres, and seeing providing my own perception on how you can use just the simple object sphere as an additional object to the original concept, which is just defining ellipse using a cone and a plane cutting through it, such that the sphere would be first copied, translated, scaled, that is, it's still the same type, that is, we can use the same properties and features, and putting this into topology map, how it relates to first with the cone itself, right, however I draw this, and how it relates to the features of the cone, that is, the tangent between the sphere and the edge, or that's the surface of the cone. That would be like the ending topology, and the beginning part of the topology where like kind of all begins is the axis, that is the center line for the cone and it goes through both spheres. That is, you're applying meta mathematics in topology as how much you can use feedback such that you are using only the basic features and definitions. Okay, I can say basic feature. Well, tangent is like a feature, right? It's not a definition necessarily, even though tangent is whatever. That you can loop within this topology. And if you can do this, then every part of this connection in that loop is equivalent to one another, right? Or let's say you can build up equivalence, and thus you can provide different abstract forms for the same concept. That's interesting. And number 2, reasoning how you can cascade this purity, perfection if you will, into second principle, or let's say philosophy of life. And the third, using errors more as triggers for abstraction in order to avoid those errors in the future that might or probably will become more as nuances, obstructions for practicality or from practicality. And all with, as we're human beings, so we have time limited in our lives, with the purpose of saving more time for us. Now, what you do with that time, if you really want to like solve this more of this abstraction, you probably, and you get positive feedback from this because it likes you, like, oh, I feel good doing this, like solving problems, then you have more time solving this and you have more, I can't say incentive, but you have more time to experience brain orgasm, if you will. And if you're not that abstract, then probably because these people also not just abstract for themselves, but they use it because this abstraction doesn't really depend on the perceiver. That is, it can be applied anywhere, right, by anyone. That is, what one person comes up with, the abstraction can now be utilized by others. Meaning that if you don't really care about how much time it would save, because you would still be wasting it on some random, I don't know, YouTube binging, then, or whatever you do, then at the very least, you can binge faster, if you will. At least you have something that you can gain from it. But for this to happen, kind of like I'm addressing myself now, right now, indirectly, but still, allow these people to abstract as much as possible so that you could be as lazy as F as possible. Okay? So don't interrupt them. Let them do the stuff. Let them do their thing. And although it's not advised to be like Isaac Newton, you know, completely isolated from the world or from people, let's say, but for the most part, people act as interruptions. I know it's a little bit off topic, but the point is, be as open-minded as possible, see how things are related on a very basic level, and you can see how equivalences just emerge on the way. Utilizing hybrid knowledge switch with transition, or let's say switching between the what's and the how of those what's being connected, or like what and connection. And if you take the connection as the equivalence and the what's as the objects or shapes you have, and types of equivalence as what an operation should add on top of these, kind of like in this point project Euler constant binary matrices. I convert binary matrices, and how you can build matrix of matrices mapped from it, and how you can, it was not there, it was my solution, and how you can transition, in a kind of primary or secondary axes, such that each axis point, or let's say axis direction, one axis has two directions, right, has one operation attached to this, and simple binary operation, switching or flipping. And if you do this, that is, again, let's abstract this again, we have different types of operations on, let's say, transitions from one representation of that object to another, and we can equalize these, or let's say we define equivalence, and we put this in topology, and we can create more abstraction. And now, if you can see those circles, like in electronics, for example, like Kirchhoff's voltage law, that is, they all converge into some kind of constant, it being it's 0 or 1 or some kind of constant. That is, you always have a reference point that is numerically addressable. Then you can apply this abstraction to many practical fields, right? And that's how you make a difference. That's how abstraction makes sense to be spent your time, even your life on. Anyways, very abstract talk, but in my imagination, like what I'm seeing in my field of view, if you will, even though I don't actually observe anything right now, it's more like just describing what I imagine. It's simple, and yet it might be like, it would be if I had actual numbers, actual functions in it, if I would just like actual proof, right? I'm just providing some kind of snippets here, like what if this, what if that. You go deeper into this, like with the conversion of binary matrices, and I saw some very unexpected patterns, which of course makes me feel good, but it all takes time. Which is why I don't provide this in camera recordings. You just have to listen and take notes, and then you can understand. Assuming you understand every word I'm saying, because if you miss a word, let's say if I say translation or a sphere, if you don't know what these things are, well, I'm sorry, but you're missing a lot. So you need some basic linguistic understanding. But this means we have syntactic mind coming to the play. So you have to balance between the purity and the practicality. In a sense, the practicality as environment providing you those errors. And thus, if you want to solve those errors, you have to generalize, and generalization happens by purity of those definitions. One example of which is just a sphere. I could say it's all connected, right? Well, yes, it's all connected, but it's deterministically connected, systematically connected. So you can reason from one to another. Not just like, oh, we have this, and then it's like a cloud of things, and just like a mesh. No. It's, as I said, feedback loops in your topology, such that the transitions form, let's say edges in the graph, would form the equivalent space, and all the nodes in the graph, or the objects, or even you could say operands, if you had like mathematical functions, would be the whats that you need to compare against one another. Anyways, my question for you, what was the last thing you did within the previous week that caused you to trigger on an abstract level? What was the thing that made you think, what if? And not like, oh, what if some event, but more like, what if we applied this abstraction to this thing, and how it relates to your own personal life? And second question, how much do you see the connection between the second principle, which is the philosophy of life, or let's say what happens within the society, and how you perceive it, or how you think you are perceived. And how all this relates to the first principles, which is, I would say, physics, because that's how the world works, right? But now I would also add math here, because that would be like a toolbox for that physics. So second principle, relation to first principle. What do you see, how you perceive life, and how this translates into the first principles. That's, by the way, much easier to learn. Okay, that's the thing. Syntactic mind makes it easier to learn because the errors you have inside in your mind, or the biases you think are true, but someone else manages to disprove that is you actually learn, right? You don't have any fixated expectations, or another way of saying being open-minded and learning from others. That is, you go from second principle to first principle, understand the first principle, and if you do it long enough, then eventually you develop this, I can say, skill, or you polish the ability to reason greater abstraction in first principle, to develop something new in this first principle domain. That is, use triggers from second principle, which means, but you have to keep your mind open, and you have to keep your eyes and ears opened. Observational input, right? Or maybe it's just my way of seeing it. Because what if you could just lay down? Actually, laying down would be quite a boring thing to do. I mean, I would rather walk and cycle outdoors at least, like, I don't know, hour a day, than just sit and read all the time. Because errors matter. As I already said, they matter for triggering, or as triggers for the overall abstraction. And they are acceptable to the point that you don't have to deal with those errors yourself manually. And now, of course, there would be like a army of engineers jumping to my neck and saying, dude, well, if you only were like this, then it would be just like an ancient Greek, right? Just philosophizing on paper. Philosophizing on paper. But it's not necessarily like that, because you have already access to the tools that engineers have created in the past, like Wolfram Alpha, for example. Or like, I'm not going to give you any very concrete examples, but you have access to so many tools that enable you to, especially if you want to prove something in math on abstract level, and you see that the errors there, I don't know, making a mistake, or seeing that, oh, it doesn't really match up, how do I add thumb of constant here that would make sense, not as thumb of constant, then those tools would become helpful, right? Like a Cox system, for example. But in general, errors in practical life are more like the blockages for train of thought. And yet when you can just observe them, you can make good use of them in long run. Both for yourself, for a momentary brain orgasm, and also in the long run for humanity, for what you have seen as an alternative representation of what can be observed, that can also be applied in real life. So that engineers can make things less erroneous in long run, at scale. And voila, we are progressing as human civilization. Isn't that wonderful? Starting from a simple thing on paper and ending with a skyscraper on top of which you are looking and observing others. Mathematician as a generalist. That would be a life well lived. Anyways, as from my side, as always, thank you for listening, thank you for watching, thank you for joining, and thank you for thinking. Bye.